Okay, so in this video we're looking at how we can work out what the mechanism for a variety of reactions is going to look like. Okay, so we're going to look at a series of rules to work out how I draw my mechanisms. Okay, and we're going to look at particular examples of mechanisms: electrophilic addition where I'm adding bromine, electrophilic addition where I'm adding hydrochloride, or an HCl, or an HF molecule, or an HBr molecule, and nucleophilic substitution reactions. Obviously, there's a free radical substitution reactions as well, but that was covered in a previous video. Okay, so we've got the rules, and the first rule is I need to understand what each of the things mean. Okay, so a curly arrow means a movement of 2 electrons. Okay, so my second rule is that I work out electron density. Okay, and I know that lone pair is greater than a double bond, which is greater than a single bond. My third rule is I look at electronegativities. And I work out electron deficiency. Okay, my fourth rule is I draw an arrow from the dense region to the deficient region. Okay, fifth is I break bonds by drawing arrows to ensure stability of compounds. And then finally I repeat the process. Okay, so if we take an example of a nucleophilic substitution reaction, okay, I know this OH, that is my nucleophile. So it has a lone pair and it's attracted to delta positives. Okay, so I work out my electron density. Do I have a lone pair? Yes, I do. Okay, so I work out my delta negatives, so I know that the carbon is more delta positive than the chlorine. So I draw an arrow from my source of electrons to the delta positive, and then I need to ensure that my number of bonds is correct. Well, that R group can only make 4 bonds, so it has made 4 bonds. So now, with this new bond coming in, I've now got 5 bonds, so I have to break the bond again to get my compound back. Okay, so then I'm going to draw what I make. Okay, right. If I look at an electrophilic addition where I've got HX, okay, so this is going to be where I've got a double bond. So for example in ethene, okay, and again I work out my electron density. Do I have a lone pair? No, I don't. Do I have a double bond? Yes, I do. Okay, I work out my electronegativities. Okay, and I realise that hydrogen is more delta positive than the chlorine. So I draw an arrow from my source of electron density to my source of electron deficiency. Okay, again, hydrogen can only make 1 bond, so I need to break that bond to ensure stability of what I'm going to make. And then I'm going to draw what I make as a product. So that double bond is now broken. So I've got a positive charge on this carbon. This carbon now has an extra hydrogen on it. So the important rule is you always add the hydrogen to the carbon that has most hydrogens already. Okay, and then I've got Cl minus. Okay, this time, do I have a lone pair? Yes, I do. Do I have a fully positive? Yes, I do. So my arrow goes from my lone pair to the positive. The important thing to notice, it does not go from my negative charge on the chloride ion. That is not a movement of a pair of electrons. Okay, and then finally, I draw what I make. Okay, the other important point to notice with these electrophilic addition reactions, we can demonstrate on bromine. Okay, so if we looked at a longer carbon chain this time, so we looked at propane, and again we had bromine in. Okay, so do I have to identify my electron density? Do I have a lone pair? No. Do I have a double bond? Yes. Okay, I have to identify my electron density. Well, in this case, there's no difference between bromine and bromine, so there's no difference in the electron density. But as the molecule starts to get closer, that repels the electron in the bond and moves the electron towards one side. Okay, so I get an induced dipole . Okay, and again, my bromine can only have one bond, so I'm going to draw my intermediate. Okay, this time, my positive charge has to go on the carbon that's going to be most stabilized. So that carbon, because it's got two separate groups on it, is going to be more stabilized. So then my first bromine is going to go on that side, and then my second Br minus, and again I can draw my arrows in, okay, and then I can finally draw my final compound. Okay, so the important thing to note there is that the positive charge was on the carbon that was most stabilized, the carbon that was surrounded by the most CH3 groups. Okay?